Okay, so last time we looked at how magnetic forces on charges end up in circular motion, how to use the right-hand rule number 2. I know you guys are all super excited about the incorporating the circular motion into this. But we're going to practice with that a little bit today. And so let's just jump right into it and work with it a little bit here. So let's get a magnetic field going. So I'm going to draw my magnetic field. And I'm going to do some double duty here, actually. First things first, we're going to have a proton coming in this way, and we're going to have an electron coming in this way. We're going to keep them totally separate from each other. We'll just use the same field for the two charges and connect things together. Let's say our proton here is coming in at, let's go with 82,000 meters per second. Let's say our field is 0.14 Teslas. Everything's coming in a right angle, so sine thetas for all our forces are going to be equal to 1, so that's fine. And let's just find a couple things. And of course, I left my or that little diagram here up from last couple times as a reminder. And we'll keep that handy as we do all this type of stuff. Okay. So let's just start one thing at a time. Let's find out the force on the proton, and let's start with that. So what is the force on the proton? Okay, now first things first, I'm going to get the direction of my force, see which way this thing is going. All right, so this right-hand rule number 2 kicks in. So my gun is going to point straight up towards the top of the screen. My 3 fingers, stretched out fingers, are going to point at me out of the screen, and that means that my force, my thumb, is pointing to the right. So my force is this way, which means my little proton here would come here and then do circular motion towards the right, and it might just keep on going, like who knows how far it's going to go, but something like that. Okay, so let's find the force on the proton. So if I do the force on the proton, okay, so force, magnetic force is equal to QVB, sine theta is equal to 1. So don't have to worry about that. So let's calculate the magnetic force on the proton by multiplying those things together. And if I do that, I get around 1.84 times 10 to the negative 15 newtons of force. So that is the magnetic force on the proton. But like we talked about last time, this actually supplies the FC for it to go in a circular path. So with that idea, what is the radius of the path of the proton? Well, that's just basic mv squared over r using our basic centripetal expression. So radius of the path would be the mv squared divided by fc, and of course that fc is being supplied by fb. So I have the mass of a proton, I know the speed, square that, and divide it by the fc, which is my fb in this case, and I can calculate the radius of the path. Let's see, that'll give me around 6.11 times 10 to the negative 3 meters, or just over 6 millimeters. Okay, and then you could also calculate the frequency and the period of the actual path, a whole bunch of stuff like that. Okay, so let's do something really, really simple. Let's use the electron now. Let's go Mr. Electron over there. Okay, let's say the electron has the exact same radius path. Okay, so what is the speed of the electron? So how fast is the electron actually going? Well, let's see if we can figure this out. Okay, now first things first, if I use my right-hand rule to see which way the electron is actually going, my electron is going to the left, so I'm going to shoot my gun towards the left. And my 3 fingers should be pointing out of the screen towards me, which means my thumb is pointing up. So if this was a positive charge, the force would be up. But since it's a negative charge, I can flip the force and it would go down. Okay, the same way if you used your left hand, you'd point your gun to the left and your fingers are coming out of the screen, your thumb would be pointing down. So it doesn't matter if you use your right or left hand, but the electron would be curving down something like this. okay, because the force is going to be down. Okay, so back to the question. The electron has the same radius path. What is the speed of the electron? Okay, well, I've got the two forces involved. I can't solve for either one of the individual forces because I don't know the V, but I do know they're equal. I know that my magnetic force is going to be equal to my circular force because it creates it. And if I do a little inventory, I know the charge, I know the B, I know the mass of the electron, I know the radius of the path. The only thing I don't know is the V, so I can solve it. Now, of course, the nice thing is this V is canceled off by that one over there, and I am left with an expression for the speed. The speed would be equal to the Q times the B divided by the radius divided by the mass of the electron. So, put in the charge of the electron, the magnetic field, the radius, and divide by the mass of the electron, and we will have the speed. Let's see, when we're all done, we should get around 1.5 times 10 to the 8 meters per second. So about half the speed of light, so we're going really, really fast. Okay, so that's how we can sort of link the two things together. Okay, so let's get rid of all this, and let's try some more practice questions. So let's try this one. Here we have an 18 Tesla field. We've got an alpha particle coming in at 3.8 to the 5 meters per second. So, of course, first things first, alpha particle, of course, the helium nucleus. So we need the charge and the mass. You guys have done this type of thing before. But, of course, the charge would be 3.2 to the negative 19 coulombs. And the mass, of course, 6.68 to the negative 27 kilograms. And we're going to find the radius and the frequency of its going around the path. And I'm going to start with my right-hand rule. My gun would be pointing to the right. My 3 fingers are pointing in the screen. So the force is up. So my alpha particle would come in and then it would curl upwards that way and make a nice circular path. Okay. So first things first, finding the radius. Okay, well, I've got my 2 forces. I've got my magnetic force of QVB is equal to my MV squared over R. I've done this type of thing before. The nice thing again, when the V's cancels out, and radius would then be equal to MV divided by QB. Okay, so then I can calculate my radius. I got my mass of the alpha particle. I know that. I know how fast it's going. I've got the charge of it. I've got the magnetic field. We're all good to go. And we get a radius of about 4.4 times 10 to the negative 4 meters. So that would be the radius of the path. Okay. So frequency. Well, frequency kicks back to your circular motion stuff. And we have the basic expression, speed is equal to 2 pi rf. You have that back in circular motion. You can easily use that here. So you know the speed, you know the 2 to the pi, you just found the radius. So you can then divide the speed by basically the circumference of the pathway, which will then give you a frequency of about 1.4 times 10 to the 8 hertz. So that would be the basic frequency of the path. Okay, so again, it's just basic circular motion stuff kicks in, and that's it. Okay, all right, let's try a different question. Okay, so suppose we have a wire. Let's see if we can put a couple things together with you guys here. We got a wire here, and let's see we got a current coming down. Okay, and let's say we got 6 amps of current going down the wire. Okay, and beside it, let's go right here, we've got an electron traveling right there for whatever reason, who cares why, and let's say it's 8 millimeters away, and let's say it's moving at 2.8 times 10 to the 4 meters per second, and we are going to find out what is the force on the electron. Okay, well, to find the force on the electron, I need to know the charge. Got it. V, got it. I need the magnetic field. So, to find the magnetic field for wire, we can use the shortcut version, 2 times 10 to the negative 7 I over R. So you can calculate how strong the magnetic field would be. And if we do that, we will get a magnetic field of around 1.5 to the negative 4 Teslas. But we also need to know which direction it's going. And if we use our right-hand rule, the first one, You know, thumb would point down for the current, fingers are pointing out around that way. So if I drew it, it would be X's on this side and it would be dots on that side. Okay. Now that I have my magnetic field, I can calculate the force on the charge. So force, of course, be QVB. I know the charge of the electron. I know how fast it's going. I found the magnetic field. And if I put all those things together, I will get 6.7 times 10 to the negative 19 newtons. Now, of course, I need to know the direction of the force. All right, so this is where right-hand rule number 2 comes in. So my gun is pointing down because that's where my electron is going. My fingers are pointing up at me because the magnetic field is coming out on the right-hand side of the wire. And my thumb is pointing to the left. Well, if my thumb is pointing to the left and it's an electron, I should flip it to go to the right. So the force would be out this way. So the electron would actually curl away from the wire. Okay, so again, so since it's a negative charge, I've got to flip the direction of my force using right-hand rule number 2, or use your left hand. Okay, so there's a couple questions with using magnetic fields and magnetic forces. Okay, and we will try one more. Okay, so we have a proton, and it's sort of going a sideways circle. So the proton's here, and it's going around something like this, making a path 0.58 millimeters wide, and it's going around 35 megahertz, or 35 times 10 to the 6 hertz. And we're looking for the magnetic field. Okay, so let's first things first, I got the frequency, so I can find the speed with the frequency, because of course speed is 2 pi RF. And of course, don't forget to change the mega into times 10 to the 6, and we can find out how fast this thing is going. And if we do that, we can find out it's going 6.37 times 10 to the 4 meters per second. So that's how fast this thing is ripping around. Okay, so now I want to know the magnetic field. Okay, so I can do that. So again, FC equals FB, so QVB is going to equal MV squared over R. Again, the V's cancel out like this. The only thing I don't have is the magnetic field. So magnetic field is going to be equal to MV divided by QR, something like that. Okay, so then we just punch out the values that we have, and we can calculate the magnetic field strength. And just be careful, use the radius, so half that 0.58 millimeters, not the full 0.58. All right, so when we calculate the magnetic field, we get a magnetic field of around 2.3 Teslas. Okay, so I also want to know what direction the magnetic field is going. So again, I can use my right-hand rule number 2 to figure this out. Now it's going in a circle, and you can pick any point you want. It doesn't make any difference. Now, I'm going to use this location on the edge here because right there I know that the proton is going away from me, so the velocity vector would be an X. So my finger gun is pointing at my screen. My force is centripetal force. I know my force is pointing to the center of the circle. So my finger is pointing in the screen, and my thumb is pointing towards the left. So that means my 3 other fingers are all pointing downwards. So this thing must be in a magnetic field that is going downwards, something like that. So the magnetic field's down. Okay, and you can pick any point you want on the circle for the pathway. You could choose right where the big proton picture is and have your gun pointing to the right and your thumb pointing to the middle of the circle, and your other 3 fingers are still going to point down. You can pick any point you want. Okay, so this is how we can incorporate circular motion into the forces of magnetic fields, and this is one of the reasons you guys didn't really do too much with magnetic fields in grade 11, because you guys hadn't taken circular motion yet, because you need to use it in order to actually look at how subatomics and charges actually move in magnetic fields. Okay, so that's how these things link together.